Hi, my name is Christopher Schulte, and today we'll be talking about lab number 2, motion of a falling object. The purpose of the lab is to observe the motion of an object that is dropped from rest and falls somewhat slowly straight down. This was carried out by using a tracking software that plot observed position versus time, and then using a computational model to create predicted position versus time graphs with and without the effect of drag to draw comparisons. The goal is to utilize physics principles and report observations on both the object's motion and develop computational models. Then we'll discuss the differences between the models and the observations made. The fundamental physics principles and models included gravitational force, which is responsible for pulling together any two objects with mass in the universe. This is directly proportional to the product of the object's masses and inversely proportional to the square of the distance between them. Earth's gravitational force, or G, is equivalent to 9.8 meters per second squared. Additionally, the drag force acts in the opposite direction of an object's motion is caused by interactions between atmospheric particles and the surface of an object. It is proportional to the square of the object's velocity. Finally, Newton's second law relates the net interaction between the system and surroundings to the observed motion or changes in momentum of the system. The acceleration of an object depends on the mass and net force acting upon the object. The system in this experiment included the falling object, which was the bundle jacket, while the surroundings included the gravitational force due to Earth and the drag force. Result: as predicted, the tracked position of the bundle jacket most closely mirrored the computational model that accounts for both the force of gravity and drag force. However, there are still somewhat noticeable differences in these two graphs, likely as a result of experimental error or imprecise measurement of position while falling. Data and analysis. Here's the tracker data from the video of the falling object. Its mass was 0.1835 kilograms, and its initial position was 1.460 meters. Because the object was falling from a vertical distance, 1.46 is put on the y component. The initial velocity was 0 meters per second because the bundle jacket was dropped from rest. The computational model excluding drag force has similar initial conditions. However, we see that the b value is equivalent to 0 because there is no drag force in this example. G is equivalent to 9.8 meters per second squared, and we were able to calculate the net force using Newton's second law, which states that net force equals mass times acceleration, or in this case, negative mg. This came out to negative 1.7983 newtons, and therefore we put that in for the net force. From Newton's second law, we derived the velocity and position update formulas in order to create the model at the left. The computational model, including drag force, is similar. However, we see that there is a b value now, which is proportional to the magnitude of the square of the velocity. In order to calculate the net force, we had to add the force of gravity and the drag force in order to calculate the total net force, and then we were able to do the velocity and position update formulas to create the model here. The equations and physics principles used included Newton's second law, from which we were able to derive the velocity and position update formulas, as well as gravity near the surface of the Earth, which is equivalent to 0 negative mg0. Weight is a constant as the object is falling, and resistance due to the drag force is dependent on the magnitude of the square velocity. Comparing all the models, we see that the initial position is 1.46 meters. However, the actual model appears to fall less distance at first, but then speeds up at a quicker pace compared to the other models. The time required to hit the ground is the largest at t equals 0.57 seconds. The predicted model without drag is similar to the one accounting for drag at first, but then deviates and falls at a quicker rate. The time required to hit the ground is the smallest at 0.544 seconds. The model with drag appears similar to the one without drag at first, but then deviates as well and falls at a slower rate. In the end, it hits the ground at a similar but slightly smaller time at t equals 0.564 seconds. Conclusions. The three principles in this lab included the gravitational force, drag force, and Newton's second law. Newton's second law that states that net force equals the summation of forces, or the gravitational force and the drag force for a falling object. Gravitational force is constant, while drag force is magnitude proportional to the square of the object's speed. From Newton's second law, we were able to derive the position and velocity update formulas. A possible source of error is inaccurate data collected from the tracking software. If it was captured from a slight angle or the quality was not adequate, the tracked position could differentiate from the actual position of the falling object. These slight accuracies could account for why the actual position versus time graph varies slightly from the computational models. Additionally, it's possible that there was a small initial velocity. The person who dropped the object's hand was not perfectly still, which could cause the graph to look slightly different. What if? In this situation, the terminal velocity would remain the same whether or not there was an initial downward velocity or not. However, it is important to note that it would take less time for the falling object to reach the terminal velocity because it had that initial downward motion. This is displayed by the two graphs below. What does it mean? Terminal velocity happens when the net force of drag pointing up has exactly balanced the force of gravity pointing down, meaning net force equals 0, there is no acceleration, and velocity remains constant. You can see this in the graph at right, as velocity appears to become asymptotic behavior, meaning to be becoming constant. Thank you very much for listening.